When Richard Feynman talks about time, he begins by quietly dismantling one of the most deeply rooted assumptions in human thinking, that time is a thing. From childhood, people imagine time as something that flows, something we travel through, something that carries moments from the future into the past. Clocks reinforce this illusion with their steady ticking, calendars give it structure, and language turns it into an object we can lose, save, waste, or borrow. Feynman approaches the idea differently. He suggests that time is not a substance moving forward, nor a river carrying events along. Time, in physics, is a method of describing change. It exists because things happen, not the other way around. To understand this, Feynman asks us to look at the simplest observations. Imagine a universe where nothing changes. No motion, no vibration, no decay, no growth. In such a universe, the concept of time would be meaningless. There would be no before or after, no sequence to compare. Time only becomes relevant when something changes relative to something else. A planet moves around a star, an atom vibrates, a radioactive particle decays. These changes allow us to compare states. Time is the label we assign to those comparisons. Clocks, in this view, do not measure time itself. They measure repetitive motion. A pendulum swings back and forth. A quartz crystal vibrates. An atomic clock tracks transitions between energy levels. Each clock is simply a system that changes in a regular way. When we say a second has passed, what we really mean is that a particular motion has completed a defined number of cycles. Time is not flowing inside the clock. The clock is changing, and we are counting those changes. Feynman emphasizes that this way of thinking removes unnecessary mystery. Instead of asking what time is made of or where it flows from, physics asks how systems evolve and how those evolutions compare. Time becomes a bookkeeping device, a coordinate we use to track the behavior of matter and energy. Just as space allows us to describe where something is relative to something else, time allows us to describe when something happens relative to another event. This perspective becomes especially important when physics moves beyond everyday experience. In daily life, changes are slow, speeds are low, and clocks tend to agree with each other. Under these conditions, time feels absolute and universal. Feynman points out that this is an illusion born from limited experience. When objects move at very high speeds, or when gravity becomes extremely strong, the rate at which change occurs can differ from one system to another. Two clocks following different paths through space can record different amounts of change. This does not mean time itself has changed as a substance. It means the processes used to measure change have evolved differently. By framing time as a measure of change, Feynman helps clarify why relativity works the way it does. In Einstein's theory, time depends on motion and gravity. Fast, moving clocks tick more slowly relative to stationary ones. Clocks near massive objects tick more slowly than those far away. This often sounds strange because people imagine time itself slowing down. Feynman reframes it. The physical processes inside the clock slow down. The atoms vibrate differently. The transitions occur at different rates. Time is not being stretched like rubber. The behavior of matter is changing. This approach also dissolves confusion about simultaneity. Two events that appear to happen at the same time to one observer may not appear simultaneous to another moving observer. If time were a universal substance flowing everywhere at the same rate, this would be impossible. But if time is a comparison of changes, then different observers, using different reference processes, will naturally disagree. There is no contradiction. Each observer is making a valid measurement based on how change unfolds in their frame of reference. Feynman often warns against mistaking human intuition for physical truth. The human brain evolved to deal with moderate speeds and familiar scales. It naturally invents metaphors like flowing time because they feel comfortable. Physics, however, demands precision. When physicists write equations, time appears as a variable, not as a thing with texture or direction. The equations do not say that time pushes events forward. They simply relate how quantities change with respect to one another. This idea becomes even more striking when considering fundamental laws. Many of the basic equations of physics work equally well whether time moves forward or backward. If time were a physical substance with a built-in direction, this symmetry would be hard to explain. But if time is simply a parameter describing change, then reversing it in an equation just describes the reverse sequence of changes. The laws themselves remain intact. Feynman's view also reshapes how we think about cause and effect. People often say the past causes the future. In physics, what really happens is that systems evolve according to laws. Given a particular state, the laws describe how that state changes. Time is the index we use to order those states. The laws do not require time to flow, they require states to be related. Cause and effect emerge from these relationships, not from a moving timeline. This becomes clearer in quantum mechanics, where change is not always smooth or predictable. At small scales, particles do not follow definite paths. Instead, physicists calculate probabilities of outcomes. Time still appears in the equations, but again, it serves as a parameter that orders events. The particle does not ride a wave of time into the future. Its state changes, and time labels those changes. Feynman is careful not to overextend this idea into philosophy. He does not claim that time is an illusion or that it does not exist. He claims that time exists in the way measurements exist. It is real as a concept tied to observation, not as an independent substance. Just as temperature is a measure of average molecular motion rather than a material thing, time is a measure of change rather than a flowing entity. This comparison helps avoid confusion. No one asks where temperature goes when an object cools. They understand that the motion of particles has changed. Similarly, asking where time goes or where it comes from may be the wrong question. The meaningful question is what is changing and how fast that change is occurring relative to other processes. When applied to cosmology, this view of time becomes even more powerful. People often ask what happened before the beginning of the universe. Feynman's framework suggests caution. If time is a measure of change, and the universe itself defines the arena in which change occurs, then asking about before the universe may be like asking what is north of the North Pole. The question assumes a coordinate that may not exist beyond a certain boundary. Throughout his explanations, Feynman returns to clarity and simplicity. He strips away poetic language not to diminish wonder, but to deepen it. By understanding time as a measure of change, we gain a more accurate picture of reality. The universe is not carried forward by time. It is constantly transforming, and time is our way of keeping track. This idea also reconnects physics with human experience in a surprising way. When people say time flies during joyful moments and drags during boredom, physics does not interpret this as time changing speed. It interprets it as perception changing. The internal processes we use as mental clocks speed up or slow down. Our brains count change differently depending on attention and emotion. Even here, time remains a comparison of processes, not a flowing substance. In the end, Feynman's explanation teaches a quiet lesson about scientific thinking. Concepts that seem obvious may hide assumptions that limit understanding. By questioning the idea of time as a thing, he opens the door to relativity, quantum mechanics, and modern physics without mysticism. Time becomes a tool, not a mystery force. It is the language we use to describe change, motion, and transformation in a universe that never stands still. Richard Feynman's second keynote idea about time centers on a powerful and unsettling realization. Time, motion, and probability are inseparably linked in the laws of nature. Time does not stand apart as a silent observer while the universe unfolds. Instead, it is woven into the way objects move, interact, and change, from the scale of planets to the behavior of subatomic particles. To understand time, Feynman argues, we must understand motion, because without motion, there is no meaningful way to speak about time at all. At first glance, motion seems simple. An object changes position, and time tells us how long that change took. But Feynman flips this relationship around. Time does not explain motion. Motion defines time. When physicists describe motion, they compare how positions change relative to one another. Time enters the equations as a parameter that orders those changes. It is not a background stage on which motion happens, but part of the mathematical structure used to describe how motion unfolds. This becomes especially clear in classical mechanics. When Newton wrote his laws, time appeared as a variable that allowed predictions of future motion from present conditions. Yet nothing in the laws suggests that time itself pushes objects forward. The equations simply relate forces, masses, and changes. Time is the bookkeeping system that keeps track of how those relationships evolve. Feynman emphasizes that this distinction is often overlooked, leading people to imagine time as an active agent rather than a descriptive tool. As physics moved beyond Newton, this relationship between time and motion became even more intimate. Einstein's theory of relativity revealed that motion directly affects the rate at which time is measured. A clock in motion relative to an observer will tick more slowly than a clock at rest. Feynman stresses that this is not because time itself has slowed down in some absolute sense. The physical processes inside the moving clock change. The atoms vibrate differently. The mechanisms evolve at a different rate. Motion alters the behavior of matter, and time reflects that alteration. This insight dissolves a common misunderstanding. People often imagine that objects traveling at high speeds somehow move into the future more slowly. Feynman points out that nothing mystical is happening. Every physical process, including biological aging, chemical reactions, and atomic vibrations, is governed by the same laws. When motion affects these laws, all processes slow relative to an external observer. Time is simply the name we give to the comparison of those processes. The connection between time and probability becomes unavoidable when physics reaches the quantum world. At microscopic scales, motion is no longer a smooth trajectory. Particles do not follow single, well-defined paths. Instead, physicists calculate probabilities for where a particle might be found or how it might behave. Time appears in these calculations not as a flowing substance, but as a variable that orders probabilities. It tells us how likely a system is to change from one state to another over a given interval. Feynman's own work in quantum electrodynamics made this relationship vivid. He showed that particles explore many possible paths, and the final outcome emerges from the combination of these possibilities. Time is not a single track that events march along. It is a parameter over which possibilities interfere, reinforce, or cancel out. Motion at this level is inseparable from probability, and time is the structure that organizes those probabilities. This view challenges the idea of a fixed, predetermined future. If time were a rigid line stretching from past to future, every event would already be laid out. Feynman's physics suggests something different. The future is a set of possibilities constrained by laws, not a script waiting to be revealed. As systems evolve, probabilities shift. Time labels the unfolding of these probabilities, not their pre-existence. Feynman also highlights that the precision of time measurements depends on the motion of the systems used to measure it. Atomic clocks, the most accurate clocks ever built, rely on quantum transitions. These transitions are sensitive to motion, gravity, and environment. When an atomic clock is placed on a fast, moving aircraft or a satellite, its rate changes in predictable ways. This is not because time itself is being distorted like a physical object. It is because the quantum processes defining the clock's rhythm are affected by motion. This reinforces the idea that time has no meaning separate from physical processes. A universe without motion would have no clocks, no transitions, no decay, and therefore no operational definition of time. Motion gives time substance, not the other way around. Time is an abstraction we use to describe how motion and change are ordered. The probabilistic nature of time becomes even clearer when considering unstable systems. A radioactive atom does not decay at a precise moment determined in advance. Instead, it has a probability of decaying over time. Two identical atoms can exist side by side, and one may decay quickly while the other remains unchanged for much longer. Time here does not act as a trigger. It provides a scale over which probabilities accumulate. The decay is not caused by time passing. It is described by how the probability changes as time increases. Feynman often used such examples to remind audiences that nature does not care about human expectations. People want certainty and precise timelines. Physics offers laws and probabilities. Time is the variable that connects these laws to observations, but it does not dictate outcomes. This distinction becomes crucial in understanding why physics can be both precise and unpredictable. Another profound implication of this view is the relativity of temporal order in certain situations. In relativity, two events that are separated in space may occur in different orders for different observers. This sounds paradoxical only if time is imagined as a single universal sequence. If time is understood as a way of ordering changes relative to motion, the paradox disappears. Different observers, moving differently, will naturally disagree about the order of distant events, because their measurements of change are based on different reference processes. Feynman's explanation avoids philosophical abstraction by constantly returning to experiment. Time dilation is not a thought experiment. It is measured using particles, clocks, and satellites. The probabilistic evolution of quantum systems is not speculation. It is confirmed by countless experiments. In every case, time appears as a parameter tied to motion and probability, never as an independent force. This approach also sheds light on why time cannot be measured with perfect precision. There is always uncertainty in any measurement of time because it depends on physical processes that are themselves subject to quantum limits. At very small scales, the uncertainty in energy and time becomes significant. This is not because time is fuzzy, but because the processes used to define time cannot be infinitely sharp. Motion and probability impose fundamental limits, By linking time to motion and probability, Feynman transforms it from a mysterious flow into a dynamic framework. Time becomes the language through which physics describes how systems evolve, how possibilities unfold, and how motion shapes reality. It is not something the universe moves through. It is the structure we use to understand movement itself. In this view, the present moment is not a vedge separating past and future. It is simply the current state of a system, defined by its motion and probabilities. The past is a record of previous states. The future is a range of possible states consistent with physical laws. Time is the coordinate that orders this progression, not the engine driving it. Feynman's insight ultimately reshapes how we think about causality. Causes do not push effects forward through time. Instead, physical laws connect states. Given one state, the laws describe how it is likely to evolve. Time is the parameter that indexes this evolution. Cause and effect emerge from lawful relationships, not from a flowing temporal current. By understanding time as inseparable from motion and probability, Feynman removes much of its mystique while deepening its significance. Time becomes a bridge between what is and what might be, a way of describing change in a universe governed by laws but rich with uncertainty. This perspective does not make time less important. It makes it more precise, more honest, and more closely aligned with how nature actually behaves. When Richard Feynman turns to the third keynote idea, he confronts what may be the most emotionally powerful aspect of time, its direction. Human experience insists that time moves one way. We remember yesterday, not tomorrow. We grow older, never younger. Broken objects do not reassemble themselves. Feynman approaches this familiar certainty with a surprising claim. The forward direction of time is not written into the deepest laws of physics. Instead, it emerges from disorder, probability, and the way large systems behave. At the most fundamental level, many physical laws do not care which way time points. If the motion of particles in a simple system were recorded and played backward, the equations describing that motion would still hold. Collisions, forces, and trajectories remain valid whether time moves forward or backward. This symmetry unsettles intuition because it clashes with everyday experience. Feynman emphasizes that the discomfort comes not from physics being strange, but from human intuition being shaped by macroscopic patterns. The key to resolving this tension lies in understanding disorder. Systems can be arranged in many messy ways, but only in a few highly ordered ones. A deck of cards can be shuffled into countless random arrangements, but only one arrangement is perfectly ordered. When a system evolves, it naturally moves from less probable states to more probable ones. This movement toward disorder is overwhelmingly likely, not because of a force pushing it, but because there are far more ways to be disordered than ordered. This statistical tendency gives rise to what we call the arrow of time. Time appears to move forward because disorder increases. When ice melts in a warm room, the molecules spread into many possible configurations. The reverse process, where those molecules spontaneously gather and form a perfect cube of ice, is not forbidden by the laws of physics. It is simply so improbable that it effectively never happens. The laws allow it, but probability forbids us from ever seeing it. Feynman stresses that this is not a matter of ignorance or incomplete knowledge. Even if one knew the exact positions and velocities of every molecule, the statistical imbalance would remain. Large systems are dominated by probability. The forward direction of time is therefore not a fundamental rule etched into the universe, but an emergent feature of large collections of particles. This insight reshapes how we think about the past and the future. The past feels fixed because it is recorded in stable, low disorder structures such as memories, photographs, and fossils. These records exist because they are themselves products of increasing disorder. A photograph forms when light interacts with a medium in an irreversible way. A memory forms when physical changes occur in the brain. These processes increase overall disorder, anchoring the past as something that has already happened. The future, by contrast, lacks such records. It consists of many possible states that have not yet been realized. Time's arrow points from recorded states to unrecorded ones, from lower probability arrangements to higher probability ones. This is why the future feels open and the past feels closed. It is not because time flows in one direction, but because probability does. Feynman also connects this idea to energy and heat. Heat naturally flows from hot objects to cold ones, never the reverse. This, again, is not due to a fundamental law forbidding the opposite, but because the random motion of particles makes the reverse process astronomically unlikely. Heat flow, like melting ice, is a manifestation of increasing disorder. The arrow of time is visible wherever energy spreads out. One of the most striking consequences of this view is that time's direction is tied to the size of systems. For very small systems, time symmetry can sometimes be observed. At the level of individual particles, processes can look reversible. But as the number of particles increases, reversibility vanishes in practice. The sheer number of possible disordered states overwhelms the few ordered ones. Time's arrow becomes unavoidable. Feynman uses this to explain why human-scale phenomena are irreversible even though microscopic laws are reversible. A glass shatters and does not reassemble because the shattered state corresponds to vastly more microscopic configurations than the intact glass. The intact state is special and rare. Once the system moves away from it, the chances of returning are negligible. This probabilistic understanding of time also clarifies why we cannot change the past. The past is not protected by a cosmic rule. It is protected by probability. To reverse the past would require an enormous coordinated decrease in disorder across countless particles. Such coordination is so unlikely that it effectively never occurs. Time travel to the past is not just technologically difficult. It clashes with the statistical structure of reality. Feynman is careful to point out that this does not mean the universe had to start in an ordered state. But for time to have a direction, some form of initial imbalance is required. The universe, early on, was in a relatively low, disorder state compared to what was possible. From that condition, disorder increased, giving rise to stars, galaxies, life, and memory. Time's arrow is therefore deeply connected to the history of the universe itself. This connection leads to a subtle but profound conclusion. The reason we experience time as moving forward is not because of how the laws of physics are written, but because of the conditions under which we exist. We live in a universe far from equilibrium, where energy gradients exist and disorder can increase. If the universe were already in a state of maximum disorder, nothing interesting would happen, and the concept of time would lose its meaning. Feynman also addresses the psychological arrow of time. Humans feel time moving forward because their brains form memories in one direction. Memory formation is a physical process that increases disorder. The brain cannot remember the future because no physical record of the future exists yet. The direction of thought follows the same arrow as thermodynamics. Mind and matter are aligned by probability. This view strips away the idea that time is a cosmic conveyor belt dragging everything along. Instead, time's direction emerges from the statistics of many particles interacting under simple laws. It is a large-scale pattern, not a fundamental command. By understanding this, many apparent mysteries dissolve. The irreversibility of aging, decay, and loss is not imposed by a cruel universe. It is a natural consequence of probability playing out on a massive scale. At the same time, this does not make life meaningless. On the contrary, it makes moments precious precisely because they are unlikely and unrepeatable. Feynman's explanation invites a quieter kind of awe. The forward march of time is not a built-in feature of reality, but an emergent story written by disorder. We are not carried forward by time. We are participants in a vast statistical process, experiencing one direction because all the others are overwhelmingly improbable. Richard Feynman's fourth keynote idea confronts a deeply uncomfortable truth. Human intuition about time is often wrong. The way time feels to us, the way we talk about it, and the way we emotionally experience it do not match how time appears in the fundamental description of nature. Feynman does not present this as a flaw in human thinking, but as a consequence of evolution and scale. The human mind evolved to survive in a narrow range of conditions, not to intuitively grasp the structure of reality at its deepest level. In everyday life, time feels smooth, continuous, and universal. We assume that everyone shares the same now, that moments flow evenly, and that the past is firmly behind us while the future lies ahead. These assumptions work well for ordinary activities, but physics reveals that they are approximations. Feynman emphasizes that intuition is shaped by convenience, not truth. When reality moves outside familiar boundaries, intuition becomes unreliable. One of the strongest intuitive beliefs is that there is a single present moment shared by the entire universe. Feynman explains that this idea collapses under careful examination. Events that appear simultaneous to one observer may not be simultaneous to another who is moving differently. This is not a trick of measurement or a limitation of technology. It is a fundamental feature of how the universe works. The concept of a universal now does not exist in the laws of physics. This realization is disturbing because it clashes with personal experience. People feel as though the present is absolute, but Feynman points out that feelings are not evidence. They are the result of how the brain processes information. The brain integrates signals over short intervals, creating the illusion of a unified present. Physics, however, deals with precise definitions, not psychological comfort. Another intuitive mistake is imagining time as something that flows. Language reinforces this idea by treating time like a substance. We say time passes, time runs out, time moves forward. Feynman warns that these metaphors can quietly mislead thinking. In physics, nothing is flowing. What flows are physical quantities like energy and matter. Time is a coordinate, a label, a way of organizing events. When equations describe change, time does not act as a force pushing things along. This misunderstanding becomes especially clear when people ask where time goes when it slows down. In relativity, time dilation is often described as time slowing. Feynman reframes this by focusing on physical processes. When a clock moves fast or sits in a strong gravitational field, the processes inside it change rate. The atoms vibrate differently. The mechanisms evolve differently. Nothing is happening to time itself. The description changes because the behavior of matter changes. Human intuition also struggles with the idea that time does not have a preferred scale. We instinctively think of time in human units, seconds, minutes, years, lifetimes. Physics, however, treats time as flexible. For some processes, meaningful time scales are fractions of a second. For others, they span billions of years. There is no single natural unit of time that the universe prefers. Time scales emerge from the processes being observed. Feynman highlights how this misunderstanding leads people to search for ultimate clocks or cosmic rhythms. There is no master clock ticking for the universe. Each clock is defined by a particular physical process. Comparing clocks is how we define time, not discovering some hidden universal beat. This realization undermines the comforting idea that the universe runs on a single schedule. Another intuitive error lies in the belief that time is independent of space. Everyday experience separates the two. We move through space, and time simply passes. Modern physics shows that this separation is artificial. Space and time are deeply connected. Changing how you move through space changes how you experience time. Feynman emphasizes that this is not philosophical speculation, but experimental fact. This connection also challenges the idea of absolute speed. People naturally think of speed as motion through space over time. But if time itself depends on motion, then speed becomes a more subtle concept. The universe enforces a maximum speed not by limiting motion through space alone, but by shaping how space and time relate. Human intuition, built for slow speeds, struggles to grasp this structure. Feynman also addresses the emotional weight humans attach to time. People fear running out of time, regret the past, and worry about the future. Physics does not validate these emotional interpretations, but it helps explain them. The brain evolved to predict and remember. Memory formation is tied to irreversible physical processes. Prediction relies on probability. These mental functions align with the statistical arrow of time. Our emotional experience follows from how matter behaves, not from time having intentions or meaning. Another intuitive trap is the belief that understanding time will reveal deep purpose or destiny. Feynman is blunt about this. Physics does not provide purpose, it provides description. Time does not care about human goals. It does not guide events toward meaning. Meaning is something humans create within the constraints of physical laws. This honesty is central to Feynman's approach. He resists the temptation to romanticize time. Instead, he finds wonder in accuracy. The fact that human intuition fails is not a loss. It is an invitation to learn. By abandoning comforting but incorrect ideas, we gain a clearer picture of reality. This perspective also reshapes how we think about free will. If time is not a flowing substance, and if the future is described in terms of probabilities rather than certainties, then human choice exists within lawful constraints. The future is not already written in time. It is shaped by present states and probabilistic evolution. Time does not trap us, it contextualizes us. Feynman's message is not that humans are insignificant or powerless. It is that the universe is not designed to fit human intuition. When we insist that reality must feel natural to us, we limit understanding. When we accept that intuition can fail, we open the door to deeper insight. In the end, Feynman's fourth keynote leaves us with a subtle shift in perspective. Time is not what it feels like. It is what it does in the equations and experiments that describe nature. Our sense of flow, direction, and urgency arises from the way our brains interact with irreversible physical processes. Recognizing this does not strip time of meaning. It grounds meaning in reality. By learning where intuition misleads us, Feynman teaches a broader lesson about science itself. Understanding often begins where comfort ends. Time, seen clearly, is not a familiar companion or a hidden enemy. It is a framework that reveals how change, motion, and probability shape the universe we inhabit.